The camera's right there. Hey everybody, it's Stephen Ramsden and Pranvera. Hi Cindy from Atlanta. We're doing a live solar broadcast, and we're going to start with white light, and we hope you enjoy it. I finally woke her up and got her out of bed and gave her some sugar, so everything's okay now. And now we're going. So here comes the screen for the white light. And what we're doing is using a 6-inch Skywatcher USA Spree refractor and a Altair 2-inch white light solar wedge. I have a green number 58 Celestron filter over a point gray Grasshopper 5 megapixel camera. My larger camera that gives me full disc is currently being serviced, so we're down to the 5 megapixel camera, which will not give me a full disc on this camera, on this telescope, but it will give me a full disc on the hydrogen alpha scope. So Pranvera is going to talk to you a little bit now while I get everything going, and she's going to talk loud because the microphone is in the computer. So there you go.
Okay. Yeah, right now we are observing the sun in the white light filter, and actually, as you can see, we don't have any sunspots today, unfortunately. The sun seems not to be very active, but probably when we observe later on in hydrogen alpha and in other wavelengths, we can see some more details and prominences. Probably, I don't guarantee, but
I guarantee it.
Okay.
We're going to see some great stuff.
So here we can see some facula. Do you call that like this in English?
Yes.
Which is right here. It's not very much visible, but you can see these white areas in the sun. And what else we can see, Stephen?
You can see the limb of the sun. The sun is always active. So this is a 870,000 mile wide ball of hydrogen plasma, and it's always active, if you ask me. And the people that always say, "Oh, there's nothing going on, it's a blank sun," I tell them to get lost, because the sun is always awesome, and it's always a good day to look at the sun. So what we're going to do is switch over to the calcium for a little bit and look at the calcium. So Pranvera is going to tell you jokes and sing you songs in Albanian while I do that. And we're going to go back to her camera so you can look at her. There she is, and me. And here we go. So I'm going to change over to calcium while Pranvera is doing her thing.
We are trying to keep with this shade so we can see the screen, and we can also protect the computer not to get overheated by the sun. So until Steven changed the camera, what wavelengths we're going to observe? Yeah, we are going to see the sun next in calcium K wavelength, which belongs to about 393 nanometers. And then probably we're going to see the sun in
hydrogen alpha
spectroscope. Yeah, in hydrogen alpha, but then we will also see in a spectroscope, which is going to be my first time to look in a spectroscope directly at the sun. I'm just excited about that. Can we bring any view from the spectroscope too?
Yes, we will be able to look at it through the cameras. And it's a L high-res 3 spectrograph.
Do you hear that? So we can also look through the camera on the spectroscope, which is gonna be nice. Yeah, we just came back with Stephen from the Georgia High Tech University. They showed us all the setup and the departments they have there. We really had great times with the teachers. And also they showed us a large number of meteorites, lunar meteorites and Martian meteorites too, and different ones, which was very neat. And they also donated a few books to the astronomy Untitled Chapter. Oh my God, this shade.
Hey, baby, will you take a couple pictures? Yeah. Oh, you look pretty.
Oh, I took a shower.
You look so hot. We have to go have sex. We'll do that.
That's terrible. All right, here we go.
All right.
Oh, move this. I'm gonna get a couple, all right?
Wait.
All right. All right, I'll try and get some over here. Y'all can choose from them.
Oh.
Okay. So we're back. Sorry about that. Well, now we're on calcium. My wife's out here with us, Natalie Anderson. She's taking some photographs for us.
Thank you, Natalie.
So here we go on calcium.
Yay.
And let's see what we got here. We are looking at, start that over again. Start video. Okay.
Great.
So,
Screen sharing.
now let me screen share. Yeah, I know. There's a lot of technical stuff going on here. There it is. All right, so we're a little overexposed, and we're coming back in just a minute. All right, you got it focused. There we go.
Yay, it's coming. Woo. Wow.
Okay, so
Look
there's
at
our
that.
calcium image. And again, I apologize. My big cameras are getting serviced, and I gave away all my other big cameras. So this is a smaller camera that I'm using while I wait for Point Grey to return the one that's being serviced. So we're looking through a Skywatcher USA 6-inch triplet at the sun. And here's a nice area of facula, the same, or plage, the same area of facula we saw on the white light scope. And let me go ahead and turn on the color real quick. And everyone can enjoy a false color image of the calcium. That color, or maybe purple.
Yeah.
Try that.
Yeah, that's it.
Yeah, it's okay. 393 nanometers, 393.4 nanometers to be exact. And this is what it looks like through a calcium K module and a Point Grey Grasshopper 5 megapixel camera. Pranvera is currently drooling. I have to get some napkins to wipe the drool off of her chin because she's watching this telescope and she wants to take it back to Kosovo with her. And let's see if we can move it up to the top a little bit. In a minute, I'll show you how to get some calcium K prominences. Pranvera has the same, basically the same equipment in Kosovo that I took there and we donated because of our awesome donors to the Charlie Bates Solar Astronomy Project.
Yeah, and I'm really impressed when I seen your image when you took it a few years back of the prominence with the calcium K, which was really large one.
Mm-hmm.
I was, amazed that we can see that through this wavelength.
That was a 3/4 prominence that was over 1 million miles long and ended up getting me as a winner in the Astrophotographer of the Year contest in 2014. I was a runner-up or something, I don't know. But that picture is now hanging at the Royal Observatory in Greenwich. My good friend Alexandra Hart beat me out of that with a better photo. But I no longer enter those contests.
So actually, before we were viewing the sun in visible light so we could see the photosphere of the sun. So Stephen, let people know what we can see through this wavelength, because probably somebody doesn't know what we are looking at right now.
We are looking at the near ultraviolet light coming from the sun. This is what burns your skin when you stand on the beach, this light. And this light is on the very edge of the visible light wavelength. It is caused by vibrating calcium atoms in the sun's chromosphere. The calcium absorbs the energy from the sun's core. The atom, one of the electrons in the outer shell of the calcium atom is expelled to release that energy. And it also releases a photon of light at 393.4 nanometers. So every bit of light you see here is being ejected from calcium atoms in the chromosphere of the sun. And there's really almost no calcium atoms in the sun. This is how bright they are. It's less than 1,000th of 1% of the sun's volume, but it puts out this much light.
So I've heard some people say that the ultraviolet radiation is much more, for example, in Australia, and it's less in Kosovo or stuff like that. Is this true?
That is correct. It is much stronger in the southern hemisphere, and there's not exact science as to why, but one of the main reasons is because the sky is so much less polluted over Australia than it is over our countries. The pollution in the sky filters out a lot of these short wavelengths. So it's really dangerous to stand outside in the southern hemisphere in South Africa or Australia, Vietnam.
It can cause cancer, skin cancer.
Yeah, well, you can die. Here in the northern hemisphere, in a city, urban area like we both live in Pristina and Atlanta, our air is so crappy and dirty that it doesn't really matter because the calcium is filtered.
Yeah, I have got some UV beads that you have got it to me, and when I was in Australia, they have turned into the ultraviolet color very fast, but it doesn't do that fast in Kosovo. So probably that's an experiment that shows us how high it's the UV.
When you hold them in your hand, the speed at which they go from white to purple determines how much ultraviolet radiation exposure you're getting. UV radiation, as they call it. And that's what skin lotion or sunscreen is designed to protect. And a lot of people call purple ultraviolet. Purple is not ultraviolet. Purple is visible light. But we represent ultraviolet in a purplish tint because the closest color that we can see is purple or violet.
Yeah.
But in reality, this light is near ultraviolet. Okay, so in real life, if you were looking at this, well, you probably couldn't see it because it's outside of the human visible light spectrum. But it would look purplish, very purple as purple can possibly be. Okay, so that's another misconception about ultraviolet. It is not purple. Ultraviolet light is invisible to us. If you're a bird, you can see ultraviolet light. But as a human, we have no need to see ultraviolet light.
I didn't know birds see that.
Yeah, birds are tetrachromatic. They can sense much wider spectrum of light than humans. And a lot of birds' markings are in ultraviolet, so they can tell sexes apart from each other. The male can tell the female by an ultraviolet stripe on their wing or something that we don't even see.
It's pretty neat.
So I'm going to turn it up a little bit so we can see if there's any prominences in calcium.
Yeah. I'm curious.
Yeah, you're going to love this if there are any, because prominences last a lot longer in calcium and go out a lot further, yes, in calcium than they do in hydrogen alpha.
Let's move a little bit in the edge so probably we can see something.
Okay.
Yeah, there's some.
Let's see if we can get a real one, a big one.
Big one.
There may not be any prominences today, but if there are, they're always more visible in calcium K
We
wavelengths
might see some tiny
than
ones.
in hydrogen alpha.
Yeah, we can solve these ones today.
So the sun is pretty quiet, you're right, but there's a nice one right there.
Yeah.
And if you turn the gamma to the right a little bit, you might be able to see that one better.
Okay, I'm going to do that.
Right, you're going left.
Oh, sorry.
What's Albanian for right?
Right.
Yeah, do that. You see it a little better with the gamma. Sensitivity turned down a little bit, now it's going away. Go back left a little bit.
We can see it. It's quite tiny, but still we can see it. It's really cool.
If you notice, you can also see the thin chromospheric ring around the edge of the disc. That's just you looking at the chromosphere from the side, and it gives you this gray ring around it. That's real visible in hydrogen alpha. But in a big telescope, you can also see it in calcium.
Like this.
So if you want to move around the edge again, you can. Or we can go back to surface detail. The sun is fairly quiet today in calcium and white light. We're using our astrophysics AP 1200 mount today, rolled out into my driveway in Atlanta.
That's a giant mount, I tell you that. Oh my god.
With a 6-inch Skywatcher USA refractor. Of course, our Coronado solar telescopes for hydrogen alpha. And we have a Sheliak L high res 3 spectrograph.
I'm looking so forward to look through that.
There's a little nub up there, not much. All right, let's swing it back down to surface detail. Calcium is really beautiful. It looks like crackle paint almost. I really like the surface detail in the calcium filter. And these areas of plage are hotter plasma. Of course, plage or plage is a French word that means beach because they thought it looked like a beach. So there you go. Now we can move around a tad and see what we got going on here. And again, this is the sun's chromosphere in ultraviolet light, near ultraviolet. And on August 21st, when the moon passes in front of this, it is going to be spectacular. So all the rookies and the once-a-year solar astronomers are out there looking at white light and bragging about their image, even though it's overexposed and out of focus. We are going to be looking at the real sun and calcium K and hydrogen alpha.
I really wanted to get my telescopes here for the solar eclipse, but to avoid the customs and everything troubles, I left them home. But
well, I'm glad you did. And hopefully one of these knuckleheads at your event will have a hydrogen alpha telescope, and it won't be just a bunch of nighttime sissy astronomers with their glass solar filters, you know. We need to get some real solar telescopes out there,
I
wherever
like to
you are.
see the totality and see the prominences at the same time with hydrogen alpha. It would be so pretty.
Actually, you can see the hydrogen alpha prominences, if there are any, without any telescope. You can just look up.
Really?
Because when the moon blocks the sun, what you're going to see is the chromosphere.
Oh my God.
The photosphere will be totally blocked by the moon. But any extended features in the chromosphere will show up to your eyes as red. Because that light's there all the time, and you can see red. The reason we can't see it normally is because the yellow and green from the sun is so bright we can't see anything else. But if you take out the photosphere during an eclipse, what you have left is anything that's in the chromosphere extended from the sun. So you don't even need a hydrogen alpha telescope to see it. You can just use your eyes.
You know,
that's only in totality, though. You can't see that in a partial eclipse. Because even if 1% of the sun is showing, it's brighter than the entire chromosphere. So in totality, look up during the totality and you'll see prominences on the edge of the sun without a telescope.
Yeah, actually, when I seen that solar eclipse in 1999, when I was 4 years old, that was about 96% covered by the moon. It wasn't all total, but it was pretty much, so it became dark enough. Right. I remember, but not so much. I didn't have to look for prominences at the time, but the partial solar eclipse we had 2 years ago, that was very good because we had the hydrogen alpha telescope you gave to us. So we could see, you know,
the donors gave to you, remember?
Yeah.
I didn't do anything. I'm just lucky enough to distribute this stuff. And Charlie Bates' monthly small donors are what make all this possible. But anyway, yeah, if you're not in totality, you won't be able to see the chromosphere. But if you are in totality, you don't need a telescope at all. Just use your eyeballs.
For this eclipse.
Yeah. So as you can see, the sky, the seeing is really terrible now because it's almost 1 p.m. here in Atlanta. It's 96 degrees on the driveway. Pranvera is wearing all black as usual because she's from Eastern Europe and crazy. And it's very, so very, very hot and very, very humid. So you can see the seeing is deteriorating rapidly in these short wavelengths. So in a minute, we're going to go over to the hydrogen alpha scope.
Yeah, let's do that.
And while I do that, I'm going to go back to watching Pranvera. And there she is. And there's me. Hey, everybody. And here we go. So Pranvera is going to tell you Albanian jokes and something while I do this.
Hurry up. Yeah, as I can see, everybody is doing preparation for the solar eclipse. I actually plan to be somewhere in Missouri to catch the totality path. And I heard Stephen is going to be somewhere in north of Georgia. So we are not going to be together for the eclipse, but I will probably try to do some live broadcasting. That is more for people in Kosovo because the eclipse won't be able or visible in Kosovo sky. So I will try to bring these people some live viewing from here. It's going to be exciting. I'm happy. And it's actually going to be the 4th solar eclipse I've seen in my life. I've seen 3 partial solar eclipses, and this is gonna be totality. It's gonna rock. Yeah, Stephen is actually changing the camera so we can bring the hydrogen alpha where we can see prominences and we can see the chromosphere of the sun again, which is about 628, something like that. Nanometer.
656.28.
Okay, yeah, 656.28, right?
Yes. You should know this.
I know that, but you know how I am with numbers. I'm getting old.
All right, so
oh my God. This shade
I'm
is
gonna try to
driving me
focus
nuts.
this thing. Keep talking. They're looking at you still. They're not looking at this.
Yeah, I know. I'm trying to see what you are doing. Do you think it's focused enough?
Maybe. We're gonna find out. It's probably too bright.
Yeah. No, it's good.
I have to adjust the Etalon a little bit.
So is this telescope double stacked? Or
Yes, this is a double stacked Coronado solar H alpha telescope. Okay? So I'm gonna adjust the Etalons a little bit, so hang on.
Okay. All right.
We always use Coronado telescopes because they're the best. Let's see what we got here. Hey, George. Turn the resolution, the brightness down a tad. Be right back. Are we screen sharing this? Hold on. Let's screen share it.
Okay. Do it.
Okay. There we go.
Yeah. I will hold the shade.
It is very, very hot here in Atlanta. And I'm having to adjust the Etalons to their extreme to even get the contrast. Let's see what that looks like. Okay, that's pretty good right there, man. That thing gives a great image, doesn't it?
Kill them.
Yeah. See if I can focus it up for you. Hold on.
Looks good.
Yeah, I think that's focused.
Looks good to me. Yeah.
Okay, so.
Wow. Oh,
All right.
okay, here we go.
Now let's turn up the gamma a little bit, sensitivity of the camera, increase the ISO, as you photographers might say. And you can see a nice filament here.
Mm-hmm.
You can see the spicule layer in the side of the chromosphere here. And if I can move all the Pranvera's selfie tools, we can see some other things.
Oh, wow.
It's a nice filament.
Yeah, and look at that. Look at
prominence.
this.
Let's go to a surface view. Yeah. And I'll turn up the exposure a tad.
I love the software.
There we go. Isn't that great? That is really an awesome view right there.
Oh my gosh.
So there's a filament up here that's about 20 times the size of the Earth. The filament is a cloud of cooler hydrogen plasma being held aloft above the chromosphere or the photosphere.
So this is actually a prominence, but we can see it from
That's correct.
another.
It is a prominence that you're looking at from the top down. And the prominence is also just a cool cloud of hydrogen plasma. This is a really interesting feature here. It's an active region, the same facula and plage that we saw on the two other wavelengths. This is the hydrogen alpha light being emitted from the same thing. And there's a nice filament zooming along there, a couple of diffuse clouds, and there's two erupting prominences coming out of that. Very thin black lines here. Those are both prominences that are sticking out of that active region. And if they were on the side, we'd see them jutting out on the side of the sun. So I'll go back to a prominence view. And we see that there's really not any prominences today. But this increased sensitivity view shows you the chromosphere from the side. And prominences, if there are any. Here's a couple up here.
Yeah, here are some.
Very small ones. There's one there.
Yeah.
Here. This is about 4 times the size of the Earth. So these features may look small, but they're actually gigantic.
We know that the sun can fit millions of Earths inside, actually, so you can just make it comparison.
What's this guy doing? Okay. So we'll go down a little bit. You still see some of the problems.
Stephen, you're gonna get all your setup, like always, to view the eclipse in that school where you're going?
Yeah, we're going to be at an elementary school, and I'll have all 7 of the Charlie Bates Solar Astronomy Project telescopes aimed at the sun, a couple of DSLRs, and about 600 screaming elementary school students, 4th and 5th graders.
Wow.
Looking forward to it. And we will see totality for about 1 minute and 20 seconds.
A minute. I think in Missouri there was like about 2 minutes or so.
2 minutes and 23 seconds is the longest it'll be anywhere in the U.S., and that's in Kentucky. And it'll be a little over 2 minutes in the center line all through the country. I'm not going to the center line because I prefer to stay at a school with kids than go and hang out with a bunch of adults. I prefer to use this as a teaching experience, so I will be south of the center line a pretty good bit, but still in totality, teaching kids about the sun. That's what we do.
I was pretty lucky to be here for the eclipse. I'm so happy.
Yeah, because you can't see it from Kosovo.
No way.
It'll just be a new moon from Kosovo, which a lot of people don't know either. I'm sorry. Yeah, a new moon from Kosovo. You know, solar eclipses only occur on a new moon.
Yeah.
If you think about it, it makes perfect sense because...
And the lunar eclipse is always in a full moon.
Full moon,
Yeah.
that's right. So, you know, the amount of things people know about the sky, especially in the U.S. these days, is really, really pathetic. Because number one, we can't see the sky from any major city because of the light pollution. And number two, no one cares. They look at their cell phone, and that's all they need to know, whatever's on the cell phone. We are encouraging everyone to look at the absolute beauty in nature that's free of charge for anyone to look at, right above your head.
So people probably might ask, because we know that the moon orbits the Earth every month and we have a new moon every month. So maybe somebody would like to know why we don't have an eclipse, a solar eclipse, each month. So Stephen, you could probably explain it better in English because my English is
Okay, well, I'll tell you
so
what.
good.
This is another thing everybody's taught.
Yeah.
They think that everything is perfect in the solar system. That
Yeah.
everything is smiling and happy and going around in a perfect circle. It's not. The solar system is a chaotic, ferociously hostile environment where things are just flying in every direction. It's basically like someone dropped a giant pile of rubble and gas and it's just exploded and it's going everywhere. So our moon does rotate and orbit around our Earth. The moon rotates the same speed as it orbits, so we always see the same side of the moon. But when it's going around the Earth, it does not go around the center of the Earth. Okay, it's slightly tilted. And then you add in the fact that Earth does not go around the center of the sun. It wobbles violently all the time, and it goes around at a slightly tilted angle around the sun. In fact, everything that orbits the sun is at a slightly different tilted angle. They're all pretty similar, but none of them are perfectly aligned. So occasionally, about every 18 months, the moon, or a portion of the moon, will pass in front of the sun from some place on Earth, from some viewpoint on Earth. So there's a solar eclipse or a partial eclipse about every 1.5 years somewhere on the Earth. So the fact that it's perfectly going to cover the sun on August 21st all the way across the entire North American continent, it's just an unbelievable mathematical coincidence. It's really unimaginable that something like that could happen because of the violent nature in which everything is just being hurtled around in the solar system. So we don't have a solar eclipse every month because the orbits of the Earth, Sun, and Moon are all tilted with respect to each other. But sometimes they all line up real nicely. And I'm going to turn on the color for this.
And you know what really amazes me? The most astounding fact that I would say...
Me and my sense of humor is what I'm guessing. No?
Actually, how astronomers can detect that an eclipse is going to happen, for example,
Yes.
in 2000 and
That's why you need
years
to
ago
learn
from
more
now.
about math.
Yeah,
Because math is infallible.
it's really amazing how they
Math
can detect in
will
what
tell you
hour and what seconds
exactly what
precisely
second.
what's going to happen.
They can even tell exactly what shape the shadow is going to be on the the Earth's surface. It's not always a circle. In fact, it's never a circle.
Gosh.
It's an oval that's wobbling and changing. And every bit of this, every little tiny piece of the edge of the solar eclipse shadow can be calculated thousands of years in advance using mathematics. And math is the language of science. So we speak math fluently here at the Charlie Bates Program. And we want you to speak math also. So there's the sun in a false color representing the actual color of this hydrogen alpha light, which is near infrared. This is the same light that warms up your French fries at McDonald's, that Pranvera knows all about, or that makes your skin hot. This is infrared light, near infrared.
So it's a long wavelength.
Long wavelength. It's also known as heat. Heat is infrared light. And that's what we're looking at, infrared light being cast by hydrogen atoms in the sun's chromosphere. So there you go, and I'm going to turn it back down to a surface view to get some of those surface details.
Wow, now I like it.
Isn't that nice? Why don't you roll around a little bit and show them the surface details, and I'll get the spectrograph ready. Walk away.
Yeah, right now we can just see more details on the surface of the sun, the disk of the sun, but we are not able to see the prominences because we have adjusted the exposure. So I'm just moving around the disk of the sun so you can see these details. Actually, Stephen is moving the telescope so
Sorry
it's
about
giving
that.
this vibration. Actually, this is my most favorite wavelength, by the way. And actually, everybody likes this most when you go out there in the public, because everybody imagines the sun, how it's like with explosions and this stuff. So everybody likes this wavelength when we show them to the public and kids. But all the time, it's not easy when you go out there with all these telescopes with different wavelengths to show the public and tell them about the sun, because you should really make it so simple so everybody, no matter what, it's an astronomer or not, should be easy to understand these wavelengths and why it looks in different colors. So what did you point at right now?
We are going to go to a view of you again so I can get the spectroscope going. We may have to do some focusing on this. I don't normally put the camera in the spectroscope, but we will give it a try. Pranvera's getting very excited, I can tell.
I am, because I was looking for this since I came over here.
We are looking at the sodium range in the spectrograph, but it is not focused. So hang on while I try to focus it.
I have a shale-X spectrograph, a small one that Stephen gave it to me when he visited us last year. He gave 3 of these to our team. So this is a much bigger spectroscope. So
yeah, it's much higher resolution, but still really cool.
Yep.
Now, let me see if I can get it focused.
Yeah, but you should screen share. Can I screen share now?
Yeah.
So let me do screen share.
You tell me if it gets better.
Okay, I will try. No.
Worse or better?
It's turning white. It's all white right now.
Okay. So when I moved in that direction, did it get worse or better?
No, this direction it became yellow again. Orange.
Okay. Just a moment.
Oh. It changed a bit the color.
Is it white?
It's orange. It's becoming white, and it changes the color often.
Okay. Just a minute.
All right.
Why don't you talk to everybody while I'm still working on this?
I don't know what to say. I'm just really excited about this spectroscope, and even though I never seen observation through a spectroscope like this, and not even through a camera at all. But spectroscopy is very important because we have telescopes where we can just see the objects and see the stars. But with a spectroscope, you can actually tell what is that star made of. And this is very good because you can understand what elements has that star or object without actually being there. So now I think it's coming out now, Stephen. Wow, just a little bit more focus. And the other side, probably. Oh, wow. Oh, yes.
Somewhere near there?
Yeah, the lines.
Okay.
Oh,
I'm
my
gonna have to
God.
try to figure out a way to make that work, so hang on.
All right. Yeah, so we will see now this emission line in
Just a minute.
every color actually represents some elements. So through these colors that we get through a spectroscope, we can know what kind of elements the sun or any other object represent, including other stars. Okay, it's fine. We still have time. We're patient.
Okay. Good. Take a little bit. Okay, so tell me if this gets any better or closer.
All right. I'll let you know. It's very faint though.
Very faint?
Yeah, should I adjust the exposure?
Yeah.
Okay, give me a second. Wow.
Sun.
Wow. It was focused before, Stephen?
It was?
Yes, it was.
Where?
Okay, a little bit more. A little bit more. A little bit. Oh, it's fine. I think it's fine now.
Okay.
Wow. Oh my God.
Okay, hang on.
This is pretty neat. Yeah, Steven will come back soon and he will let us know more about this equipment. It's actually my first time to see a spectroscope like that, so I'm not very much familiar with that, but he will let us know about this equipment and who it's inside, how it works, and then what we can understand through that more.
Good.
Yes, I think it's focused now, so...
I should be moving through different wavelengths then.
Yeah, I see now it's green.
Which way is it going?
It's going...
What color is it?
It's green right now. It's still green.
Okay.
Green. Still green. It's turning to blue.
Blue?
Yeah.
Okay. So come here, let me show you something.
Yes. Wait a second, everybody.
This thing right here, turn it this way,
Yeah.
it goes to the ultraviolet, and if you loosen it, it goes to the infrared. So I'm going to narrate it and get you to turn it, okay? So you have to reach there and turn it.
All right. You let me know when.
Okay. All right, so I've got Pranvera up here doing spectroscopic duty. She's going to tune it, and I'm going to tell you what we're looking at. Okay, so this is in the green to blue range. Okay, so turn it Pranvera?
Okay. Tell me if I'm doing it too fast or something.
That's good. All right. Stop. All right. So this is in the blue or the indigo region. Every one of these black lines represents an absorption line from an atom in the sun's chromosphere, absorbing light and then re-emitting the light. And this is a 2400 lines per millimeter resolution grating. So we're seeing an extraordinarily close-up image of the sun. And I'm going to record this just for my own fun so I can save it. So everybody hang on just a minute. Just a second. All right. I'm going to start recording this. Okay, so here we go. Frame. All right. Pranvera, keep going in like that. Now we're getting more towards the violet. All right, stop right there. Okay, this is a particularly interesting line. It's very thick, which means there's a lot of it going on.
Let's see that. Wow.
Okay, this is a thicker absorption line. These indicate the amount of the reaction absorbing the light that's happening. So it's usually because of more of the atom or because it is a more violent reaction. None of these lines are curved. They're all straight. And if they get curved sometimes near sunspots or things, the magnetic or the absorption lines can actually bow like this because of magnetic fields. And that's called the Zeeman effect. It was discovered by a scientist named Zeeman. And that's how they found out the sun was a magnetic field, a giant electromagnetic field. Because these lines can actually be curved by strong magnetic fields. So we're going to go further over to the ultraviolet area. And unfortunately, one of us has to turn the spectroscope while the other one narrates. So you're getting me. Keep going, keep going. There's another pretty thick line. Keep going, keep going. We've seen a lot of these tiny lines are caused by iron atoms in the sun's chromosphere. A lot of people think that there's a thing where people think if you have iron in a star, it collapses or something. That's not true. There's iron in every star's chromosphere. It's when you start to produce iron in the core is when the supernova occurs and you collapse. There's a ton of lines over here in the near UV. Keep going, keep going. All right, slow down a little bit. Look at all these lines here. Come here, look at this, Pranvera. See how closely spaced all these lines are? We're getting into the near ultraviolet now. Okay.
Wow.
Most of these lines are caused by electrons in the iron atom. There's a lot of iron in the sun's chromosphere. So go ahead and keep turning, and I'll tell you when we get to the calcium K absorption line. I hope you guys are keeping up with this. It's pretty interesting stuff, really. There's also a helium line over here. It's really good. See how it's almost going away? All right, stop.
Yep.
We are near calcium K, but as you can see, the camera's not sensitive to that wavelength. It doesn't see it very well.
Wait, just one spot.
That's the actual sun. That's the sun right there. It's showing you a picture of the sun. When you look through a spectrograph, you get the object in the center, and then you get the spectral lines around it. So that's because we're pointed directly at the sun. Okay, so we can't see the calcium K line because the camera is not very sensitive to it. So we're going to go the other way now, and I'm going to show you.
Let me know where to stop.
Yeah, turn it the other way. You can go pretty fast. Going through the violet. Now we're going to hit the green here in a minute. All right, stop. Go back the other way just a little bit. Stop right there. Okay, this is the magnesium triplet. These are 3 lines that are always together and that always indicate magnesium atoms in the sun's chromosphere.
Does this ever change?
Yes, if there's a strong magnetic field, it will change. Or if suddenly there was no more magnesium in the sun, it would go away. But anything that produces these lines at these wavelengths is magnesium. Count on that for sure. That's called science. So this is the magnesium triplet. And now we're going to keep going the same way. We're going to go to the sodium doublet next, which are 2 lines that are very close together that are always indicative of sodium. Going the wrong way.
Really?
Yeah.
Oh, geez.
She's from Kosovo, man. She can't understand English. Okay, keep going, keep going. You're going to see it start to turn a little yellow here in a second. Keep going. All right, go a little bit the other way, just a little bit. All right, right there. These 2 very dark lines are caused by sodium atoms in the sun's chromosphere. This is the sodium doublet. Okay, and I'm showing you all the markers in the spectrum that scientists use to calibrate the spectrum. And that's the sun. Okay, so these are the sodium doublet lines, and they're always in the same spot. Now we're going to go through and find the hydrogen alpha line. Okay. And of course, hydrogen alpha is our favorite line in solar astronomy. The hydrogen alpha line is part of the Balmer series. See, we're turning all red. We're getting close. We're in the near infrared. And it's a really big fat line. You can't miss it. Stop. Go the other way a little bit. Right there. Okay, so this is the hydrogen alpha absorption line at
Wow, you have a picture of this in your slide, I think.
656 nanometers. I do. I give this lecture all around the country and the world.
Yeah, you give it in close.
And everybody kind of scratches their head when I talk about this stuff because it doesn't make any sense to anyone.
It does.
But in reality, Pranvera, spectroscopy is astronomy. That is where all the data comes from in astronomy. This spectrograph has more data in it than every telescope, optical telescope on Earth combined.
I told earlier the telescope just helps us to see objects, but the spectroscope can us understand what is inside.
Yeah, it analyzes the composition, the temperature, the radial velocity, the motion, the distance. Yeah, this device has, like I said, more data in it than every optical telescope on Earth combined.
So tell me, through the spectroscope, is there a way where we can see the whole the whole colors?
Yes, but you have to take the spectroscope apart and put a lower resolution grading in it.
Oh, I see.
Because right now, I have a 2400 lines per millimeter. And the more lines per millimeter you have, the farther it spreads the spectrum across. So if you go down to a 300 lines per millimeter, you'll see the entire visible light spectrum right there.
So the spectroscope has a prism. What kind of equipment, devices have inside?
Spectroscope allows the light in from the sun, and it has a diffractive surface.
Yes.
Okay? And there's a diffractive, well, first off, there's a slit where the light goes in. A tiny mechanical slit cut into a piece of metal, and this one's 24 microns across. So that reduces the light down to a usable amount. And then that light is projected onto a reflective surface that has lines etched across it. Okay? And those lines are the 24 micron lines. They're spaced 24 microns apart. And what that does is creates a diffractive surface. So it's not reflecting off that surface, it's diffracting. And when it diffracts, it spreads the light out based on its wavelength. The longer wavelength light travels slower, and the shorter wavelength light travels faster. So you end up getting the colors spread apart by this diffraction. And then that diffracted spectrum is sent into an eyepiece or a camera, and you look at it. So that's exactly how your handheld diffraction grading works, or the paper ones I give away to kids, and that's how this spectrograph is working. And you can attach sensor devices that measure just the amount of light at different wavelengths, and that'll give you a graph across the screen. And that graph is where all the data is that will tell you what temperature it is, how fast it's turning. Every bit of data you could possibly learn from an astronomical object is gathered using spectrographs and photometry. It's not pretty, and you're not going to get a bunch of 8-year-old students to get excited about it. But actually, you really should, because once you learn what it is, it's way more interesting than astronomy.
So actually, as we are here at the wavelength of different colors, we know that we see the sunset and the sunrise in red color, but when it's up in the sky, it's more yellow and other colors. Correct. Also, the lunar eclipse looks, when it's full, I mean a lunar eclipse, the moon looks red, and this has to do something with this, right?
Yes, it does. The atmosphere of the Earth is comprised of certain chemical composition, mostly nitrogen and oxygen. And when sunlight travels through that atmosphere, if the sun is directly above you, it's traveling through much less atmosphere. So when the sun's directly above you, the yellow light makes it through around the body of the sun and just directly around the sun. There's a lot of yellow glare that gets through. Blue light gets through across the rest of the entire sky. So the blue around the sun, when it's directly above you, people would say the sky is blue. The sky's not any color. That's sunlight you're seeing that's being spread through the atmosphere. The blue light goes a lot farther than the yellow light.
This is really cool.
Now, when the sun gets down to the horizon and you're looking sideways through the Earth's atmosphere, you're looking at 1,000 times more atmosphere than you were when it was above you. So what that does is filter out all the color almost. It filters out everything except for the very long wavelengths of reds and oranges. So that's why you'll still see a little bit of yellow in the center of the sun on the horizon, but all around the edge of it, it's no longer well. It's just red and a little bit of orange. So that's how that happens. Now, when you have a lunar eclipse, the sunlight is passing through the Earth's atmosphere on the edges of the Earth, and that red scattered light is projected onto the face of the moon.
So I bet if moon had an atmosphere, the solar eclipse we would see, it would, it would do something similar.
It would be a different color, depending on what was in the atmosphere. Wow. Yeah. I mean, that red light is always hitting the moon, but when the sun reflects off the moon, it blocks out all that red light because it's not bright enough. But when the sun is not hitting the moon, like during a solar eclipse or lunar eclipse, then you can see the red light bouncing off the moon. It's always there, but you can only see it when the main sunlight is blocked by the Earth during the lunar eclipse.
So I hope you don't mind that I'm asking you many questions, but I bet even everybody who's listening is also curious to know. But spectroscopy is also very important when we discover exoplanets. So would you tell us why exactly and what we can do with the spectroscopy when we discover exoplanets?
You bet you. Yeah. Several things. Number one, you detect an exoplanet now because of a dip in the light emitted at different wavelengths. So when you're looking at a star and you see its light changing, dipping and rising at different wavelengths, that's indicative of an object passing in front of the sun or the star, causing its light to reduce. So that's one way we can discover exoplanets and discover that there are exoplanets. Another really cool thing about spectroscopy, which is my lecture tomorrow night, by the way, is that you can tell the speed at which these exoplanets are moving around the sun based on the red shift and the blue shift in the spectrum. Something else, you can look at the sun and tell. You can tell the rotational velocity of the sun by looking at the left side. It'll have a blue shift, and the right side will have a red shift. It's going away from you, but the left side's coming towards you.
I didn't know.
So you can tell the speed of the movement of the sun based on how much the spectral lines are shifted left or right. And you can also use that to tell rotational velocity of galaxies or any other object in the sky. Okay.
So this is how they discovered the Andromeda is coming toward us.
Yes, absolutely. It's going. Yes. Another really cool thing is when that starlight passes through the atmosphere of that exoplanet, it will give you a very faint reading of the composition of the atmosphere of the exoplanet. Because you take a reading of the star without the planet in front of it, you get its exact composition and temperature. And then when you see the light dip from the planet passing in front of it, you take another reading and you'll see things in the spectrum that weren't there before, like hydrocarbons or perhaps oxygen or liquid water. You know, every molecule or atom produces a spectral line. So you compare what's there now versus what was there when it was just a star, and anything new is part of that planet.
Oh my God.
And you can tell the atmospheric composition of the exoplanet by reading the spectral line. And look, man, you guys can do this at home. Tom Field is probably the leader in the world on spectrographic software. He has a program called RSpec and a star analyzer that you can hook to any crappy telescope or camera and plug it into your computer, and you can take spectral lines of a galaxy or Betelgeuse or anything else from your driveway in no time. Very, very simple software.
It's really getting me excited. I really, like this. And thanks a lot, Stephen, for informing me for these things. And also,
you heard it right, folks. This is the United States of America, and there's a young college girl, attractive young college girl, who is interested in spectroscopy. I just wanted to make sure you heard that.
So actually, how do scientists detect the temperature of the star or sun through the spectroscopy?
Well, there's something called the black body radiation curve. Okay, and that is a standard curve that tells you what temperature something must be in order to emit a certain wavelength of light. The sun's photosphere is 5,500 degrees because on the black body radiation curve, the light that's emitted at yellow, the temperature must be 5,500 degrees for that wavelength to be produced. Okay, so matter will emit light. Like if you heat up a rock on Earth to 700 degrees Celsius, it will emit red light. We know that, okay, because that temperature is red. The temperature of the light indicates the color it will be. So whatever you see, wherever its spectral peaks are, tell you what the temperature of that item is. We call that heated rock lava, by the way. The volcanic lava is red because it's a certain temperature. If the volcano heated the rock hotter, it would be white or yellow.
So this is why they say that the blue color it presents very high heat, so that's why the blue stars are the most heated in the
Yes. And remember, heat and temperature is just the measurement of how much an atom is shaking. Movement of atoms. That's what temperature is. If the atom's just barely moving, it's going to be cold. When you heat it up, you're adding more energy and it moves faster and faster and faster, vibrates faster, and it produces shorter wavelength emissions. Makes perfect sense, which is bluer.
Yeah.
Okay? If you freeze it, it emits longer wavelengths. Okay? Until you get all the way down in the radio waves and stuff, microwaves. Very long wavelengths. Sub-millimeter, they call it. So, unless something's at absolute zero, which hardly anything is, it's emitting in a form of electromagnetic radiation. So even an ice cube is emitting radiation because an ice cube is 32 degrees Fahrenheit or 0 degrees Celsius, but absolute zero is minus 254 degrees.
So when you make
an ice cube is actually pretty damn hot.
For example, when I turn this on, which I can, you can see that the flame is more yellow up and it's more blue in the end. Does it mean that the end is more heated?
Yeah, because that's where the source of the fire is. It's hotter when it first comes out and then it cools off as it goes out. So it's blue in the bottom and then yellow at the top because this isn't as hot as that.
It's really neat stuff.
Color.
Always, everything is science, my
Color
goodness.
equals wavelength. Wow. And color is directly determined by the temperature of the object emitting the color. Basic physics.
This is very good. I really
Learn some math, Mona. Get on it, okay? We're never going to get to Mars if people watch Kim Kardashian and The Real Housewives. So I guess that does it for our broadcast today. The Pranvera's had a great deal of fun. I'm going to go ahead and turn off this
Thank you very much to everybody for watching us. And Stephen, thank you very much for your time. I'm really happy I was able to view through your telescopes and spectroscope, which I was very curious. And thanks for letting me know many new things.
It's my pleasure. Let me turn off the screen share and come out here, and here we are. So we are in Atlanta, Georgia, in my driveway, and this is Pranvera Hassani from Astronomy Outreach of Kosovo. And I'm Stephen Ramsden, the director of the Charlie Bates Solar Astronomy Project. And we are trying to teach science, dude. That is the way we're going to survive, okay? The human race has got to explore space and get out there. And I want to thank Celestron, Meade Instruments, Coronado Telescopes, Skywatcher USA, and Rainbow Symphony for
And everybody else who's supporting Charlie Bates.
being sponsors of our program. Pranvera is here because of your small monthly donations and sponsorships. And we have less than 4% admin costs for the last 10 years. Nobody makes a dime, unfortunately. And everything goes to students like young Pranvera. She's a model of our program. So thanks for watching, man, and so www.solarastronomy.org. Bye.